All right, let's start. So, hello everyone, and thank you for attending my talk. I'm Bangjie from National University of Singapore, and it's a real honor to be here today. I'm presenting our work, CAMPrints, leveraging the fingerprints of digital cameras to combat image theft. On behalf of my co-authors, Choon from NUS and Joon from KAIST. Protecting the copyright of online images has been a long-standing challenge. With the rise of social media and photo sharing platforms, image theft, or the unauthorized use of copyrighted photos, has become even more common. And this leads to serious financial losses for photographers and image agencies. Imagine a scenario where Charlie shares some of his photos on a platform like Instagram. Meanwhile, an attacker, and let's call her Mallory, downloads or takes a screenshot of one of those photos, edits it, and then reposts it on her own social media account. So how can social media platforms help Charlie fight image theft? One way is to search their image database, which are consistently collecting photos across the web, and search for content that looks similar to Charlie's. But even if they found a suspicious match, how can they tell whether Charlie is the original owner of the image? And this is where Charlie's camera can come in. This camera that took the photo can act as a physical proof of ownership. And this is like the physical tokens that banks give out to verify your identity. And it turns out that tiny imperfections in camera's hardware leave unique traces on the photos it takes. And these hardware traces can be used to identify the exact camera that captured the image, like a hardware fingerprint. And the camera fingerprint can help provide physical evidence of image ownership. And out of all the components in a camera, the image sensor leaves the most distinctive trace. And this trace is called photo response non-uniformity, or PRNU. And this appears when uniform white light hits the image sensor. So in an ideal case, if every photodiode were perfectly made, they produce the same voltage, resulting in identical pixel values across the image. But in reality, slight variations in electrical properties could cause each photodiode to respond a bit differently. So this leads to small differences in pixel values, creating a unique noise pattern, the PRNU-induced noise pattern. What's more important is that this noise pattern is embedded in every image, and the same sensor should produce similar patterns regardless of whether the image has been processed or not. That said, using PRNU to identify cameras is not really a new idea. There has been quite a bit of research in this area. Now let's walk through the general process of PRNU-based methods. Now, suppose Charlie provides a photo taken with his iPhone. By analyzing the image in the frequency domain, these methods generally extract the PRNU pattern, and this serves as the reference. Then they extract PRNU patterns from any suspicious image and obtain a test pattern. Next, they compare the test and reference to check for similarity. If this similarity exists a certain threshold, we can say the images are likely coming from the same camera. However, current PRNU extraction and matching methods still have some limitations. One key limitation is that PRNU matching is highly sensitive to geometric changes or distortions. Let me show you a few examples. These are examples of geometric transformations, such as affine and projective transform. And these are examples of distortions, such as barrel distortion. And these could be transformation functions applied to the images. Now, let's take a closer look with a simple experiment. We apply 3 different edits to an image and then extract the noise patterns. These are the noise patterns. In case you cannot see the changes clearly, we also provide the corresponding RGB images for illustration. So test A shows color effects, test B shows geometric distortion, and C shows simple cropping and resizing. You actually notice that B and C, the similarity drops below the threshold. causing the match to fail. And this happens because these methods assume the reference and test patterns are perfectly aligned in space. But in real-world cases, that's often not true, right? Because attackers could freely edit the images. Hence, we ask the following question. Can we detect image theft even when attackers could freely edit the images? Let's begin with the threat model. The attacker's goal is to modify the image to evade detection while maintaining its visual content and quality, preserving its economic value. We assume the attacker has access to image editing tools and evaluate image against detection mechanism. However, the attacker does not apply transformations that entirely change or regenerate the image. This excludes the use of generative models, such as diffusion models, and extreme image processing techniques like aggressive downsampling. Next, let's see how our approach, CAMPrints, can help address image theft in real-world cases. Suppose Charlie shares photos on social media that incorporate CAMPrints. The system periodically scans for potentially suspicious image, and we refer to this process as coarse grain detection. It relies on image content and may yield false positives. And this is very similar to Google image search. I believe everybody uses it. At this point, CAMPrints' core technique can take over in the fine grain detection stage, analyzing the PIU-induced noise patterns of the suspicious images to verify whether they originate from the same camera. So if a match is found, Charlie is notified of the potential theft. Now, let's zoom in into CAMPrints' core technology. The core idea behind CAMPrints is inspired by how humans recognize images. Just as a person can identify a cat despite geometric transformations or distortions, CAMPrints applies the same principle to the PIU patterns. We employ representation learning to create compact clusters for each camera, regardless of the applied transformations. For a simple illustration here, even when different transformation functions, such as F1, F2, and F3 are used, the resulting point could still form tight clusters. However, the idea is simple, it is not easy to do it, and we have encountered several challenges. First, since the attacker can freely edit images as long as the content and quality remain intact, we must account for a broad spectrum of editing types, parameter settings, and their combinations. For instance, iOS alone offers over 20 editing options, even with more available in tools like Photoshop. Second, the noise pattern contains not only the sensor noise, but also content-induced noise. For example, in the noise pattern shown here, the edges of the letter S are still visible. And these edges and textures represent unwanted content noises. What we actually need are the sensor noises usually found in uniform regions, such as the white background. So separating content-induced noise from sensor noise is not trivial and requires special design considerations. So, to address these challenges, CAMPrints follows a two-phase approach. During training, social media platforms could use public image datasets labeled with corresponding camera IDs. The data processing module applies image edits and form data triplets to train two models. The first one is a denoising network that extracts noise patterns from RGB images, and a CNN encoder that maps these patterns into compact latent representation. Now, in the verification phase, CAMPrints compares embeddings from suspected images and user-provided references to identify a match from the same device or different device. So if a match is found, then we alert the user. So let's zoom into how we tackle the challenges. So to address challenge number one, we begin by applying image editing operations to the dataset. And these transformed images are then fed into deep learning model to help it adapt to various transformation functions, F1 through Fn. However, exhaustively covering all possible image editing, which are Fns, types, parameters, settings, and combinations will be computationally infeasible. Instead, we focus on selecting a small yet representative subsets. Our approach starts by categorizing editing effects into 3 groups. The first one is pixel value changes, which refer to color alterations. The second is pixel location shifts, which affect the position of image content and key points, such as mountain tip. And the third is operations that involve both effect 1 and effect 2. Now, we want to quantify effect 1 pixel value changes using color histogram differences before and after editing the image. We then quantify effect 2 pixel location shifts by measuring the motion vector magnitudes. Each pixel location shift will form a motion vector, and we can measure the direction and magnitudes of these vectors. With the quantification of effects, we can then map each image editing operation into a 2D feature space, with the x-axis represents the location shifts, and y-axis represents the value changes. Now, each operation appears as a color circle in this space. For example, A could be crop plus resize, B could be color effects, F could be geometric distortion. And to identify representative edits, we select those with the widest coverage, choosing the largest spanning circle to effectively fill and represent the diversity of this feature space. For instance, we can begin with selecting operation A. Then we choose the next operation to fill up the remaining uncovered region in the feature space. We can select B, E, and F. So this set of A, B, E, F is one of the representative sets, while other alternative sets are possible. We then train a deep learning model to extract the noise pattern from RGB images. However, this noise pattern extractor captures both content and sensor noises, leading to our second challenge. To address this challenge, we designed an embedding extractor. Specifically, it encodes the noise pattern into a latent representation, aiming at 1, filtering out content-induced noise, and 2, maximizing similarity between features from the same device. And to achieve this, we use triplet contrastive representation learning, incorporating special design considerations tailored to our needs. First, we carefully control the image content within the triplets. The anchor holds the reference image content, while the positive sample is chosen to have as different content as possible, but they're from the same device. And then, the negative sample is selected to have content as similar as possible to the anchor, but they are from different devices. Now, by maximizing the similarity between the anchor and positive samples, and minimizing it between the anchor and negative samples, the model is encouraged to disregard content-induced noise and focus mainly on the sensor noise. Second, the triplet loss optimization enhances feature similarity for images from the same device, even after image editing. Initially, processed images may fall outside the cluster of unprocessed images and processed images from different cameras, and they can overlap, and it's an undesirable outcome. So our goal here is to form 2 distinct clusters representing each device, regardless of processing or not. So triplets, in this case, helps to achieve this goal by pulling together processed and unprocessed images from the same device, while pushing apart images from different devices. So I have now given a brief overview of our system design. For more details, please refer to our paper. So now let's shift focus and take a look at the system performance. We evaluate CAMPrints using an image data set along with the corresponding camera IDs. To access instance level accuracy, we ensure at least 3 different device instances per make and model. In total, the data set includes 5 brands, 8 make and models, and 36 device instances. The model is trained on only 4 operations and tested on 40 additional operations and their combinations. So in summary, CAMPrints achieve an average area under the ROC curve, or AUC, of 0.92, outperforming baseline methods by a factor of 1.8. It is compatible with existing PINU extraction techniques. It is robust to number and order of image operations. It generalizes well to on-scene image operations, as well as commercial software. Additionally, it produces 80% fewer false positives compared to reverse image search, just like Google Image. Now let's take a look at our overall results, and for further details, please refer to our paper. So we compare CAMPrints with baseline methods across 3 different scenarios. First, when the image editing operations involve only value changes, such as auto-adjust and preset filters, and we call it ops value. Second, when only spatial transformations are used, such as crop, rotate, or perspective transform, we call it ops location. And third, a combination of both are used, and we call it ops both. The AUC is used as an evaluation metric on the y-axis, while both CAMPrints and the baseline methods perform well in the case of ops value. CAMPrints shows notably stronger performance in the ops location and ops both, significantly outperforming the baselines. So now let's move on with several discussion points. We envision CAMPrints being integrated into social media platforms, photo sharing services, and copyright monitoring tools like Pixie and TinEye. CAMPrint can also offer promising avenues for further development. First, CAMPrints could be combined with digital tokens, such as invisible watermarks, to enhance copyright protection. Second, it could contribute to the development of open standards for digital content authenticity and provenance, such as C2PA. Finally, CAMPrints' core technology may support law enforcement and investigators in online media forensics by helping identify ownership of inappropriate or illegal content shared online. In conclusion, with CAMPrints, a system that detects online image theft using camera fingerprints as a physical evidence of ownership, we aim to inspire future research in digital content authenticity and provenance. That concludes our presentation. Thank you. And we welcome any questions from the audience. By the way, I'm on the job market. You can scan the QR code for my personal webpage. Yep, thank you.
We have time for about 2 questions.
Thank you.
Great talk, very interesting work and great presentation. This is Leming from Hong Kong PolyU. And I noticed that you mentioned that you can extend your work with invisible watermarks. So I'm curious that what if I directly apply the invisible watermarks?
That's a great question. So as I keep mentioning in my talk, so basically what we want to do is to really provide a link between the physical world and the cyber world, right? So that's we call physical tokens, right? So basically the ultimate goal here is to use your camera as a physical token to prove that, hey, this image really belongs to me, and I have an evidence, which is physically here. While image watermarks are digital. They exist in the cyber world. However, it could be a good complementary solution to camera fingerprints, right? So we are actually currently exploring the coexistence of camera fingerprints and invisible image watermarking. Thank you.
Okay, I see. And another question is, what if the attacker uses his camera to capture the image? So the image will contain the attacker's CAMPrint. Yeah.
So let me clarify your question. So are you asking the attacker can gain access to the, let's say, Charlie's camera?
Yeah. And I mean, so for example, he sees the image of Charlie online, and he uses his camera to capture the online image so that the captured image will contain the CAMPrint of the attacker's phone.
I see. Yeah, I get your question. So in this case, basically, this is actually out of the scope of our use case scenario, because basically what we are envisioning is direct reuse of your photos. The reason is that basically the ultimate goal of an attacker is to earn money from reusing your photo. So if I just take an image from a screen or a projector, the image quality is significantly reduced. So in this case, the attacker might not have or do not have the incentive to do this.
Okay.
Yeah,
Okay.
thank you.
Thank you very much.
Thank
We
you.
have time for one more quick question, and the next speaker can come and set up.
Miles from UC Irvine. Thank
Hi.
you for the very interesting talk. So I wonder, is your system still going to work if like some kind of lens filters are being used? Like some, like some photographers, they prefer the usage of certain lens filters under certain circumstances, right? So yeah, I just wonder if the system would still work.
Sorry, I don't really catch your question. Could you repeat it?
So basically, for example, for DSLR cameras, those professional cameras, they sometimes put some kind of lens filter. Like for example, there's this some kind of brightness reduction filter, lens filters,
Yeah,
like
I see.
lens add on to the lens filter add on to the lens of the camera.
All right, yeah, I got your question. Thank you for your question. Yeah, that's also a great question, because what if we just change the lenses and we just apply a filter on the lenses, right? So will our system still work? So in our scenario, it works. The reason is that because by applying a color filter, it's essentially, applying colors, right? Color effects. Not exactly the same, but it's very similar. So in some case, as long as the camera fingerprints remaining inside the image, we are able to do it. However, you might envision some cases where the camera fingerprints are completely gone, right? In such cases, the image quality is significantly reduced. So do I answer your question?
Yes, I wonder if you had the chance to test this.
In our experiment, we only tested the software-based color changes, but for the all right, so I guess the only evidence we have here is that we actually test different lenses, but we didn't really apply filters on it.
Okay.
Yeah,
you.
we do have some tests on the lenses, but we don't really have a filter on it. Yeah,
Thank you.
thank you.
Let's thank the speaker again. Our next speaker is Nan Jiang. Nan Jiang is a PhD student at the University of Chinese Academy of Science. Her research focuses on mobile security and trusted execution environment. Today, Nan will be sharing about their work on the TEE on